Hello, and welcome to Differential Equations. This is lecture 36, the wave equation. Last time, we talked about the non-homogeneous heat equation. This time, we want to talk about a different partial differential equation. So, the last couple lectures, we've seen how some of the ordinary differential equation tools we've developed allow us to solve the heat equation Next, we'll consider another of the most important partial differential equations. Let's consider a flexible elastic string stretched tightly between supports that are fixed at the same horizontal level. Right, so it's a simple picture. So here's the x-axis, and we've fixed a string along the x-axis at x equal to 0 and x equal to L. If the string is set in motion, at some initial time t equal to 0, for example, by plucking it, and is then left undisturbed, it will vibrate freely in a vertical plane provided that damping effects such as air resistance are neglected. Let's consider the forces acting on a small piece of string between some point, say x, and x plus delta x. and assume each point on the string moves solely in a vertical line. Let u of x comma t be the vertical displacement and let's let capital T of x comma t be the tension in the string and let's let rho denote the mass per unit length. Of the string. Okay, so to analyze what's happening, we will apply Newton's law. Right? Newton's law saying that F is equal to ma with F the force from the tension which applies tangentially. Right. So if you picture the little piece of string being like this, that at any point the tension is being applied tangent to the string. And so it's convenient to imagine a little triangle here with angle theta. Yeah, I don't know if you can see that. Let me make a bigger triangle. Angle theta, so this is the angle relative to the horizontal. And let's split up the components of the tension. H of x comma t will be the horizontal component, so that would be capital T times cosine theta, and V of x comma t, the vertical, so that would be T times sine theta. So these are the horizontal and vertical components of the tension. Okay, the first thing to notice is that since there is no horizontal acceleration, the net horizontal force which would be capital H of x plus delta x minus capital H at x, this has to vanish. Right, which tells us that H of x comma t is actually just H of t. It is independent of x. On the other hand, the vertical acceleration, right, is given by the second derivative of u with respect to t, right, evaluated at some point. So it's not surprising the second derivative with respect to time, right, because it's always the case that if you have position, then one derivative gives you velocity and the second derivative gives you acceleration. Now we're evaluating this at some point x bar comma t. Here, x bar is the center of mass of the piece of string. Between x and x plus delta x. Okay, so that's the vertical acceleration. The mass of this piece of string is rho, right, the mass per unit length, times delta x. Hence, for the net vertical force, we have v of x plus delta x, comma t, minus v of x, comma t. This would be equal to rho times delta x times the second derivative of u with respect to time evaluated at x bar comma t, right? If we put the delta x on the left-hand side, then this takes the very suggestive form where the left-hand side looks like the limit you need to take to get a derivative. So now let's take a limit. We let delta x go to 0. And the left-hand side becomes the derivative of v with respect to x at the point x comma t. And the right-hand side becomes rho times the second derivative of u with respect to t, evaluated at x comma t. So here the difference is that x bar, which was some point in between x and x plus delta x, if you let delta x go to 0, that point has to converge to x. Okay, so far so good, except the left-hand side is in terms of v, and we want it to be in terms of u. So we just need to rewrite capital V in terms of u. Okay, so if we go back to the picture, V is the vertical component of the tension, right? This graph here that we drew the tangent to, that's the graph of u. And so the slope of this tangent is the derivative of u with respect to x. And the slope of this tangent line in terms of theta, that would be tangent theta. So if I want to isolate tangent theta, notice that if I divide this right-hand side by this right-hand side, I will exactly get tangent theta. So that says that if I do v of x comma t, and if I divide by h, which remember only depends on t now, then I get tangent theta, which is the slope of the tangent line the graph of u, and so that's du by dx. So that means that capital V is capital H of t times du by dx. And the equation becomes derivative with respect to x of h times the derivative with respect to x of u is equal to rho times the derivative of u with respect to t squared. Finally, we'll assume that h over rho is a positive constant, which will denote c squared, and we arrive at two derivatives of u with respect to time equals c squared times two derivatives of u with respect to x. This is the one-dimensional wave equation. Notice that we say one dimension and we mean one spatial dimension, right? Because of course there's two dimensions here. So there's t and x, right? The one dimension refers to the x. In higher dimensions, the wave equation is, for example, three spatial dimensions. You would have second derivative of u with respect to t is equal to c squared times second derivative of u with respect to x plus the second derivative of u with respect to y plus the second derivative of u with respect to c. The constant c is known as the wave velocity. Okay, so as we just saw, in one dimension, the wave equation is modeling the movement of a string where, for example, you fixed the two endpoints and then you've plucked it, right? In two spatial dimensions, the wave equation would be modeling the motion of a thin elastic sheet, for example, the head of a drum, right? So you bang a drum, the head starts shaking, and that's modeled by the two-dimensional wave equation. Interestingly, this equation models many physical situations, including waves in the ocean, acoustic waves in the air, electromagnetic waves in the atmosphere, all sorts of wave-like phenomena. This equation was introduced by Jean-Leconte D'Alembert in 1747. And so often this right-hand side is known as the Laplacian, but if you take the left-hand side minus the right-hand side, then that's often called the D'Alembertian, after D'Alembert. D'Alembert was a French mathematician who lived from 1717 to 1783, right? So he died the same year that the American War of Revolution ended. Interesting about his name, D'Alembert's mother was a former nun who had what has been described as a brilliant social career in which political intrigues and amorous liaisons contended for first place. And this mathematician was the product of one of these liaisons. On his birth, he was left on the Church of his Steps. Blech. On his birth, he was left on the steps of a church. He was taken to an orphanage, and since the church was Saint Jean le Rond, he was named Jean le Rond. He later gave himself the last name of d'Alembert. You may have heard of him because he, together with Denis Diderot, was the editor of the famous Encyclopedia of the French Enlightenment. So he introduced this equation precisely to study what happened when you plucked a string. He made an interesting study of music, in fact. And he noticed there's a simple trick for solving the one-dimensional wave equation. So what we'll do is we'll define the new variables psi equals x minus c times t and eta equals x plus c times t. And then we'll use the chain rule to rewrite the wave equation in terms of these variables. Okay, so how does the wave equation come in? Well, the derivative with respect to t is going to be the same as the derivative with respect to xi times the derivative of xi with respect to t plus the derivative with respect to eta times the derivative of eta with respect to t, right? Which works out to minus c times the derivative with respect to xi plus c times the derivative with respect to eta. And then the derivative with respect to x similarly breaks up into the derivative with respect to xi times the derivative of xi with respect to x plus the derivative with respect to eta times the derivative of eta with respect to x. And that works out to derivative with respect to xi plus the derivative with respect to eta. So if you put these together, then the wave equation becomes, well, we start with the derivative with respect to t of u squared. And so that's equal to, so d by dt squared. So I'm going to square this. So I'm going to go ahead and pull out the c. So I'll get c squared. And then other than that, when I square this, I get derivative with respect to c squared minus 2 times the mixed partial plus the derivative with respect to eta squared, all of that applied to u, right? And we want that to be equal to c times the second derivative of u with respect to x, right? So I can write that as c squared, and then to find the second derivative with respect to x, I'm going to take this and square it. So I end up with derivative with respect to c squared plus 2 times the mixed partials plus the derivative with respect to eta squared, all of that applied to u. And now let's stare at this. So I have a c squared and a c squared. Second derivative with respect to each of these variables. So those cancel out. And all that we're left with is minus 2 times the partials and plus 2 times the partials. So if I put those all on the same side, I would end up with 4 times c squared times the mixed partials, all of that equal to, applied to u, equal to 0. So that's the same as just having the second derivative of u with respect to c and eta is equal to 0. Well, this is a dramatic simplification. And we can solve by integrating twice. Once in eta, say, and then in c. Right? So let's do that. If we start with second derivative of u mixed partials equal to 0, and I integrate once with respect to eta, then on the left-hand side, I'm going to, by the fundamental theorem of calculus, just get rid of the derivative with respect to eta. So I end up with first derivative, right? And this is a function of c and eta. On the right-hand side, if I integrate 0, I get a constant, okay? But I'm integrating with respect to eta. So I get something that's constant with respect to eta, right? But it could still depend on c. So I end up with an arbitrary constant in eta, so that's just an arbitrary function of c. And now I integrate both sides with respect to c. So I end up on the left-hand side, just u. On the right-hand side, I have the integral of f of c dx plus an arbitrary constant, but this is now a constant with respect to c, so that means it's an arbitrary function of eta. Let's call it phi of eta. And then the integral or the antiderivative of an arbitrary function of xi is just another arbitrary function of xi. So let's call that psi of xi plus phi of eta. Switching back to x and t, we see that the solution of the wave equation is u of x comma t equals psi of x minus ct plus phi of x plus ct. Okay. So notice that this is, we can think of this as a wave psi traveling to the right at speed c plus a wave, the phi, traveling to the left at speed c. So this is really remarkable. Usually, for a partial differential equation, you don't expect to be able to just write down the general solution. right? We've been able to do that for some ODEs, but PDEs are much more complicated. So it's really surprising that you can just write down the general solution. Of course, we need these functions to be twice differentiable in order to be able to plug them into the equation, but that's okay. Assuming they're twice differentiable, you can plug them in and they will satisfy the wave equation. Now here, what do I mean by waves traveling? Well, I just mean as t changes, right? If you have some profile for one of these functions, let's say that the graph of psi looked like that, then as t increases, you would see this moving to the right, right? It would be the same graph, just translated to the right at speed c. And similarly, whatever profile you have for phi, you would just see that moving to the left. Okay, so that's wonderful. There is a general solution. However, when you're interested in boundary value problems, you don't make use of this general solution because it's not convenient for fitting the boundary conditions. Instead, for boundary value problems, it's convenient to use separation of variables. Like we did for the heat equation. Since the wave equation is second order, in both x and t, we need to specify two boundary conditions. Right, so typically one at x equal to 0, one at x equal to L, and two initial conditions at t equal to 0. So for example, u of x0 equals f of x, and the derivative of u with respect to time at x0 is equal to g of x. And the boundary conditions, we're typically, in fact, for us, we're just going to study Dirichlet. Dirichlet boundary conditions correspond to a vibrating string, like we talked about before, which is held fixed at the endpoints, right? Or if you were in two spatial dimensions, to a drum head, right? The drum should be fixed at its boundary, and then you vibrate the drum head. Neumann boundary conditions wouldn't be very natural for describing a string because you wouldn't be fixing it at the endpoints. But it would be natural if you were describing, say, a wind instrument, right? If you have Neumann boundary conditions, then what you're asking or what you're imposing is that the mean displacement of air particles during tone production is at a local max or min at the end of the flute or whatever wind instrument you're looking at. Okay, so let's go back to the example we discussed to derive the wave equation. So consider a fixed string plucked at time 0 and then released. So that means that we're going to have some initial f of x, but g of x is going to be 0 because we just release it. We don't continue exerting any force on it. So that means the equation we're looking at is two derivatives of u with respect to t equals c squared times two derivatives of u with respect to x. Subject to, and so we're going to impose Dirichlet boundary conditions at x equal to 0 and at x equal to L. And then we're going to impose our boundary condition, our initial conditions, u of x 0 is f of x, and du et at x 0 is going to be 0. Okay, so we can go through the separation of variables argument again, like we did for the heat equation, or recognize that Dirichlet boundary conditions correspond to Fourier sine series. And look for a solution of the form u of xt equals sum beta n sine of n. Let me give myself more space. Beta n of t times sine of n pi over L x. So we look at the boundary conditions in x, and they're homogeneous, Dirichlet, and so we know that that leads to the Fourier sine series. So let's go ahead and assume that our solution has the form of a Fourier sine series, where the coefficients, right, they're constants with respect to x, but that means that they could be functions of t, and we want to figure out what those functions are. Since we're writing u like this, let's also write f as a Fourier sine series. I'd say f of x is equal to sum n goes from 1 to infinity of phi n sine n pi over L x. Okay, so now that we've done that, let's substitute our guess into the equation, right? Now, when we do this, we don't need to write down these Dirichlet boundary conditions because we've already chosen to use the sine series, and so these will automatically be satisfied, right? So we just need to write the other conditions. Okay, so first the equation. Two derivatives of u with respect to t. Okay, well, if we've decided that u has this form, right, then this would be two derivatives of beta times sine pi over x. And now we want this to be equal to c squared times two derivatives of u with respect to x. Okay, so if we're guessing that u is going to have this form, then this would give us c squared times the sum n goes from 1 to infinity of beta n of t times minus n pi over l squared sine n pi over l x. Okay, so that's the equation. Next, let's look at these initial conditions. So we have u of x comma 0. So if I put in t equal to 0 here, I end up with sum n goes from 1 to infinity, beta n of 0 sine of n pi over lx. And I want that to be equal to f of x, and f of x has this Fourier sine series. And then the derivative of u with respect to t at x comma 0. So that would be the sum n goes from 1 to infinity of beta n prime at 0. I want that to be equal to 0. So these are the equations we want to solve, right? Since we know that these signs, these are eigenfunctions corresponding to distinct eigenvalues, so they are orthogonal. So this gives us an equation for each beta n. We have beta n double prime is equal to minus c squared n squared pi over l squared beta n, right? From comparing the coefficients here and here. And then this equation tells us that beta n at 0 is equal to phi n, and that beta n prime at 0 is equal to 0. Okay, so if we look at this equation, this is now an ODE, constant coefficient, linear. So we know exactly how to solve it. We look at the characteristic equation. Right, which is r squared plus c squared n squared pi over l squared equal to 0. So the general solution is beta n of t would be some constant, let's say capital E, times sine of c n pi over l t, plus some other constant, let's say capital F, times cosine of c n pi over l t. Actually, we usually put them in the opposite order. Let's do that. So first cosine and then sine. Doesn't matter, but let's do that. And we need beta n of 0, right? So if we plug in t equal to 0, then sine of 0 is 0, cosine of 0 is 1, so we get e. That should be equal to phi n. And beta n prime of 0. So the derivative of cosine is going to be minus sine. Evaluated at 0, you get 0, so this isn't going to matter. And then the derivative over here, we would get f times c n pi over l times cosine. Cosine of 0 is equal to 1. So we just get this, and we want that to be equal to 0. So since Cn pi over L is not 0, that tells us that f is equal to 0. Thus, we have found that beta n of t is equal to phi n times cosine of Cn pi over L t. Okay, and finally, this yields the solution to the wave equation. U of x comma t is equal to the sum, n goes from 1 to infinity, of phi n cosine of Cn pi over L t times sine of n pi over L x. Right? So let's scroll back to the equation we started with. Right? You have the wave equation with Dirichlet boundary conditions and these initial conditions, right? So we're just plucking the string, but not imposing any force at time 0 and derivative. And the solution is, well, take f, write it as a sine series, right? And then using those coefficients, phi sub n, you can write u as phi sub n times cosine c n pi over lt times sine n pi over lx. Okay, let me finish with a remark, because we said the general solution of the wave equation was a difference of two waves, one traveling right and one traveling to the left. So notice that if we use the identity cosine of an angle times sine of an angle is equal to 1/2 of sine of the sum of the angles minus sine of the difference of the angles, we can rewrite the solution as u of x comma t is equal to the sum, n goes from 1 to infinity, of phi n divided by 2 times sine of n pi over L x plus ct minus the sine of n pi over L x minus ct. And so we see a wave traveling to the left and a wave traveling to the right, just as we expected. Okay, and we'll stop there for today and pick it up next time.